And welcome back to College Algebra. Today we're going to talk about P4, rational exponents, and radical expressions. I expect this section will have 3 videos as well. We'll probably finish all the theory in the first video here. The rest of the videos will all be exercises, because there's quite a few different exercises we need to go through dealing with, especially the radical expressions, the roots, and a few to deal with in the rational exponents. So let's get going. Radical or root expressions. If you have a positive integer n, that's called the index of the root, then the principal nth root of a is defined. You have the nth root of a equals b, means that b to the n equals a. We know the square root of 4 equals 2 because 2 squared equals 4. Similarly, the third root of 27 equals 3 because 3 raised to the third power equals 27. Roots are in essence inverses of exponents. An exponent will take a number times itself a certain number of times. A root will find the number that if you multiply it by itself that number of times, it will equal the number you're trying to take a root of. So the nth root of a is b. Now, we do have some caveats here, because if you have an even index number, you do have to have a positive. The number inside here is called a radicand, but a positive argument or expression inside the root. The reason for that is fairly easy to see if you think about square root. Let's look at the square root of negative 4. If you think about that number, you're trying to find a number that if you multiply it by itself, you get negative 4. But we're only dealing with the real numbers so far, and the real numbers break down into 2 groups, positive numbers and negative numbers. If you multiply a positive number times itself, you get a positive number. If you multiply a negative number times itself, you get a positive number. Thus, there's no real number you can multiply by itself and get a negative number. And that's what I'm saying down here. An even root of a negative number is not a real number. It's still a number. I forgot. A number, but we haven't defined what type of number it is yet. That'll be the basis of complex numbers and imaginary numbers later. Should be around chapter 3. But for right now, nth root of a equals b means b to the n equals a. That's true for any root. Now, this symbol, if you have an even root, there are actually 2 even roots of every positive number. Sure, if we were looking at the square roots of 4, 2 is a square root of 4, but also negative 2 is a square root of 4. So you might ask, well, why, when I do this, don't I say plus or minus 2? Well, that's because this symbol means the principal nth root, and the principal is the positive nth root of a. So when you see square root of 4, it would be in error to say it's negative 2. It's only positive 2 when you use this symbol. Similarly, the cube root of 8. Oh, sorry, it doesn't matter for odd exponents. Similarly, the fourth root of 16 is 2. Even though negative 2 is also a fourth root of 16. It's just these symbols, these radical symbols is what they're called, denote the positives root of the number. If you want to talk about the negative root, there's no symbol for it, but we don't really need one. If you want to talk about the negative square root of 4, you just find the positive square root of 4 and stick a negative on it. Pretty simple. Alright, moving on from there, we have some properties of these roots. Here are 5 properties. We'll use the first 2 quite a bit, the third one not so much, and the last 2 quite a bit. First one just tells you that if you have a root around a multiplication, such as AB there, you can split the root or distribute the root. So if I had 4 times 3 inside a root, a square root, I could distribute that to both pieces and get 2 root 3. That would be an acceptable work. And you can do similar things with divisions. Sometimes it'll actually go either way. Sometimes you'll want to take a root that's on a fraction and split it. Sometimes you'll have 2 roots and you'll want to make it a single root, so maybe you could reduce the fraction or something. This is kind of an interesting property here, even though we may not use it that much. It just says if you have, say, the square root underneath a cube root of 2, remember the square root, even though it's not written, would have an index of 2. So if I'm going to apply that rule, this would be the same thing as a single root of 2, but to the 6th root, because I'm just multiplying the 3 and the 2. Now this is a very interesting set of conditions down here. It may seem like if you have the nth root of a to the n, it would always just be a. That makes a certain amount of sense because roots and exponents are opposites. If you do one and then the other, the operations should reverse each other. Well, these examples show pretty well why that happens. If you have an odd root, there's no big deal because there's only one odd root of everything. There's only one cube root because cubing preserves the sign. You can take a cube root of any number, whereas an even root of only positive numbers. Because, say, the cube root of negative 27 is negative 3, whereas the cube root of 27 is positive 3. Here, you can see cube root of negative 5 cubed is negative 5. Now this is tricky, because if you take the 4th root of negative 3 to the 4th, well, if you think about what an even root does, sure, it'll take negative 3 to the 4th. I'll even give you that value. That would be 81. So we'd have the 4th root of 81. Now, if it were a perfect inverse, it would take it straight back to negative 3. But remember, that isn't what this sign does. This gives the positive 4th root. So the positive 4th root of 81 is 3 again. So that's why if you have an nth root of a to the n and you have it inside an even root, it's going to act like an absolute value because the root's only going to give back the positive number. So if it started out negative, it's going to end up positive. If you want to stop the video at this point and go look for some of the exercises we did with radicals, that would be fine. I'm going to continue on and talk about the rational exponents, which will only be a slide or two. And then we will go on to the exercises after that. Rational exponents. This connects the radical expressions, the roots we've just been dealing with, to exponents. As we noted on the last slide, the properties of radicals look like some of the rules of exponents. That's no coincidence, because as we see here, we can write radicals as exponents. If you want to take the nth root of a number, it is just a to the 1 over n. That's why on our standard graphing calculator, there's not going to be a button necessarily for the nth root, because you don't need one. If you want to take 8 cube rooted, you can literally just use the exponent key in your calculator. 8 to the 1/3. And it will give you back 2. Furthermore, you can mix and match powers and exponents. Here's a full fraction with something other than 1 in the numerator. And with that, the numerator of the fraction corresponds to a power. The denominator corresponds to a root. So if I took 8 here and I raised it to the 2/3, that would tell me, work on my 3 there, that would tell me to cube root 8 and then square it. Or vice versa. Get the same thing either way. If you cube root it first, you get 2. You still have to square it, and that's equal 4. If you square it first, you get 64 to the 1/3. And then if you cube root 64, you get 4. May or may not know that, but 4 to the 3rd is 64. 64 is kind of a special number in that way, and that is the third power of 4, the square of 8, and the 6th power of 2. And again, because we're dealing with roots, this has to be true. We have to have the radicand, the variable inside the root, must be positive if we have an even root, because otherwise we're not going to get real numbers. And I think that's all the theory for this section. So we're going to look at some exercises next, and I expect I will have to divide the exercises into 2 videos because there's quite a few we need to get through. So I hope you enjoyed the video. I'll talk to you again when we get to the exercises.